November 15th, 1942, 1 a.m., 8,400 yards south of Savo Island. The mighty Japanese battleship Kirishima moved quietly through the dark. Her crew was very sure of their excellent night viewing gear and years of tough training. On her command deck, Captain Sanji Iwabuchi gazed through the best sighting devices money could buy. These tools had given Japanese gunners a huge edge in earlier sea fights. What Captain Iwabuchi did not know was that 8,400 yards away, an American battleship had been watching his ship for the last 7 minutes. Not through spyglasses, not through floodlights, not through the fine Japanese light-based tools his Navy had spent 10 years perfecting, but through hidden electronic eyes that could see through the dark, smoke, and rain. Before we continue, show your support by subscribing and letting me know where you're watching from. These eyes were sending exact distance, direction, and speed facts right into machine-run computers that moved the gun barrels with a straightness no human could ever match. The USS Washington began shooting at 1 a.m. 16-inch shells screamed into the night. At least 9 hit her. Some reports, based on Japanese ship repair notes and wreck checks, suggest 20 hits. In just 7 minutes, Kirishima's steering wheel locked up. Her main guns went silent. Huge amounts of water threatened to flip her over, and fire ate up the top parts of the ship. By 3:25 a.m., she rolled over and sank, taking 212 sailors with her. 1,098 people were saved. Captain Iwabuchi lived through the sinking. His final message to Admiral Nutaki Kondo claimed his guns had landed shots on the American battleship. He truly felt this was true. In the mess of the night fight, with shells passing overhead and his ship falling apart around him, he had no way to know that every one of his shots had missed. The American ship had never come close enough to be seen. She had simply shown up from nowhere, fired with terrible accuracy, and vanished back into the dark. The USS Washington, led by Rear Admiral Willis Augustus Lee, Jr., had not been struck. Not a single Japanese shell had found its target. This was not luck. This was the power of radar-guided shooting working against an enemy who could not see the ship that was firing at them. Washington's Mark 8 radar had followed Kirishima without stopping for the whole battle, sending facts to Mark 1A computers. These machines figured out the shooting angles faster and more correctly than any human crew could have done. This kind of success was not supposed to be possible. Japanese Navy rules, built on many years of experience and practice, believed that night fighting belonged to the side with better sighting gear and more practiced lookouts. By every measure that mattered back in 1941, the Imperial Japanese Navy had both advantages. Yet here in the waters off Guadalcanal, something basic had changed. The Americans had rewritten the rules of sea war, and the Japanese were only starting to understand that the whole game was different. The truth would take months to fully sink in. The size of America's technology lead was so huge, so hard to grasp, for minds shaped by many years of Japanese progress, that even when Japanese officers held the proof in their hands, they struggled to believe it. The story of how the American Navy jumped 2 years ahead of its Japanese partner is not just a tale of one new item or one sudden success. It is the story of 2 industrial ways of thinking crashing together, 2 ways of fighting meeting, and one nation's steady underestimation of a foe they had written off as soft and unprepared. Japanese certainty in their Navy's strength had deep roots. Since the Russo-Japanese War of 1904 to 1905, the Imperial Japanese Navy had grown a culture of excellence built on strict training, clever battle plans, and new technology. Their officers spent years learning the tricky parts of fighting at night, firing guns by sight, and using torpedo methods. Their sailors trained hard on seeing ship shapes, guessing distance, and quickly setting guns. This practice brought real results. Japanese lookouts could tell what a ship was from farther away than their American opposites. Japanese gun crews could shoot straight faster after finding a target. Japanese torpedo teams had created the Type 93 Long Lance torpedo. This weapon could hit ships 44,000 yards away while moving at 38 knots. It was pushed by oxygen instead of compressed air, leaving no clear trail. It carried a Ford 90 Keyless warhead, more than twice the force of American torpedoes. The Long Lance showed the Japanese Navy's main idea. Take an item they already had, make it perfect through careful work, and use it with crews trained to take every possible advantage. In fight after fight during the first year of the war, this way of thinking brought wins. At Savo Island in August 1942, Japanese cruisers had badly defeated a group of Allied ships, sinking 4 large cruisers in less than an hour of night fighting. The win came from better training and better tactics. But the Americans were fighting a different kind of war. While Japanese Navy progress focused on making what they had better, American progress focused on changing the most basic rules of sea combat itself. The difference was not clear to Japanese watchers until it was too late. The start of American Navy radar began not with military needs, but with scientific curiosity. In the 1930s, scientists at the Naval Research Lab in Washington studied how radio waves travel. They found that ships bounced radio waves back in ways they could sense. This was interesting. What made it a game changer was the steady American method of turning a lab idea into a useful military tool. By 1940, the USS New York had run the first successful trial of radar-aimed gunfire. The system was rough, needing many people to run it and lots of hand-done math, but it worked. Guns could be pointed at targets too far away to see. This got the attention of Admiral Ernest King, who would soon be the main commander of the U.S. fleet. He knew that radar wasn't just a small step forward, but a complete change in sea warfare. King pushed for fast new invention and use. His idea was not just to put radar on old ships, but to use radar in every part of the Navy's work. Finding things, tracking, gun control, finding the way, directing planes. Every job that used human eyes could be made better or done by electronic tools. The job was huge. Radar technology in 1940 was still being tested. Making it strong enough for war needed them to fix thousands of engineering problems. Making it small enough to put on a ship needed tiny parts that pushed the limits of what factories could make. Making it straight enough for fire control needed a carefulness that was beyond most pre-war factory standards. The Americans fixed these problems not through one brilliant person, but through well-organized factory work. The Massachusetts Institute of Technology Radiation Laboratory started in October 1940. Within a year, it had more than 4,000 scientists and engineers working there. Over the course of the war, this single lab would create over 100 different radar setups, each made for a special battle use. The radiation laboratory showed the American genius for managing large projects applied to warfare technology. Scientists from schools across America came together in the campus labs in Cambridge. Physicists who had spent their careers studying hard ideas now focused on real-world uses. The lab ran on rules that seemed messy to the old military research, but it got results with amazing speed. Research groups worked at the same time on linked problems. They liked competition between groups, and successful fixes were quickly shared across all teams. Failures were studied, and lessons given out in days. This created a new kind of work environment where a success in one area helped progress in nearby fields. The lab's output was incredible. Mark Viv radar for tracking planes, Mark 8 for surface ship gun control, Mark 12 for better surface tracking, Mark 22 for close-up anti-aircraft work. Each system fixed a specific need found from the fleet's reports. When battle reports showed faults in the current systems, engineering teams changed the plans and tested fixes in weeks. Factory teamwork was part of the research from the beginning. lab engineers worked straight with factory partners to make sure plans could be made in large numbers. Test versions were checked not just for how well they worked, but how easy they were to build. Parts were the same across many systems to make building and fixing simpler. This method meant lab breakthroughs got to the fleet faster than Japanese systems moved from a test version to the first round of making. Japanese radar research stayed mostly in schools until 1943. Very smart scientists in university labs made real steps forward in parts technology. But the organization that could move these steps forward into ready-to-use fleet systems did not exist. Research stayed separate. Different labs fought for limited money instead of working together. The connection from lab to factory to fleet was never built with the careful, full plan Americans achieved. This was American factory power in its strongest form. Japan had brilliant scientists. What Japan lacked was the large-scale factory setup to take brilliant ideas and turn them into thousands of the same units used across a whole fleet. The difference was not in science skill, but in using it in a large, planned way. The Mark 8 fire control radar began service in mid-1942. It could track surface targets 25,000 yards away in total darkness, giving distance, direction, and speed change with enough accuracy to guide the main guns. The system was not perfect. Early versions suffered from signal mixing and wrong readings. But American rules allowed for not being perfect if the system worked well enough to give a battle edge. The Japanese way of dealing with technology demanded perfection before it could be used. This meant Japanese radar invention, though smart in some science areas, fell behind in real-world use. Japan had created a 10-centimeter cavity magnetron by 1939, a big achievement. But their desire for perfect engineering held up its use until systems met too high reliability levels. By the time Japanese radar reached the fleet in large numbers, American systems had gone through many new versions. The gap was growing. American radar development was not a single plan, but dozens of efforts side by side, each sending improvements back into the factory base. When Mark 8 radar showed limits, engineers created Mark 12 with better target separation. When Mark 12 proved not enough for anti-aircraft work, they created Mark 22, made specially for tracking planes. Each new version took months, not years. Each fix was sent out across the fleet as fast as ships could be updated. Japanese Navy technology progress could not keep this pace. Money and materials were limited. Factory ability was used up building ships, planes, and guns. Radar work was given to many competing research groups with little shared effort. There was no group like the Radiation Laboratory, no central push forcing steady improvement across all uses at the same time. The result was that by mid-1943, American surface fighters usually carried many radar systems, each made for a different job. SG surface search radar gave the big battle picture far away. Fire control radars guided guns. Air search radars found coming planes at distances that allowed their own patrol planes to be directed correctly. These systems were connected through plotting rooms where workers put together electronic facts into a full understanding of the fight. Japanese ships in the same time period usually had only one radar system, if any, used mainly for early warning. Connecting it with weapon systems was minimal. Gun control stayed mostly sight-based. This meant Japanese ships in night battles were fighting partly blind against enemies who could see perfectly. The Battle of Guadalcanal showed this difference with harsh clarity. Rear Admiral Lee led Task Force 64, built around battleships Washington and South Dakota, protected by 4 destroyers. His job was to stop Japanese help from reaching Guadalcanal. Spy reports showed a strong Japanese force coming, centered on the battleship Kirishima and many cruisers under Admiral Kondo. Lee was uniquely skilled for radar-aimed night fighting. Before the war, he had won 5 gold medals in shooting at the 1920 Olympics in Antwerp, showing the careful skill and math that would shape his command style. More importantly, he had been involved in radar work and testing from the earliest days. He understood the power and limits of the equipment in ways most commanders didn't. He had studied the technology, taken part in trials, and grasped both its possibility and its rules. This knowledge gave Lee something rare among Navy leaders. In 1942, it was confidence in systems that seemed almost like magic to others. He trusted the technology enough to fight based on electronic facts rather than just seeing things. Lee had done practice drills using radar for gun control. He had seen the system work in tests. He knew that radar could give correct firing angles at distances where light-based systems were useless. This knowledge meant he was ready to use abilities other commanders might have been too careful to trust in a real fight. Lee's force made contact at 11:17 p.m. on November 14th. SG radar found Japanese ships over 18,000 yards away. Lee waited to fire, letting Japanese forces get closer while his fire control radars locked on and figured out the firing answers. This needed self-control. His crews could hear Japanese forces coming through sound gear. Lookouts tried hard to catch visual sight, but Lee trusted his radar to tell him the right time to fire. Japanese forces, using only their eyes to find targets, did not know they had been seen and followed. The Japanese force split, trying to attack the sides of Lee's group. This move, which was smart against an enemy using only sight, was useless against radar tracking. Lee's plotting rooms kept perfect knowledge of where the Japanese ships were. At 1:00 a.m., with Japanese ships 8,400 yards away and still unaware of Washington's spot, Lee gave the order to shoot. Washington's main guns spoke first. 16-inch guns firing based on radar math in total darkness. The shots hit. Kirishima's upper deck burst into flames, giving the first sight confirmation of her spot to Japanese watchers. But by then, it was too late. Washington's fire control radars stayed locked. Shot after shot crashed into Kirishima with machine-like accuracy. The Japanese battleship tried to shoot back. Her sight-based rangefinders struggled to find Washington through the dark, smoke, and sudden rain. The few shots Kirishima managed were bad guesses based on the flash of Washington's guns. None found their mark. In 7 minutes, Kirishima was battle-destroyed, stopped dead in the water with major damage. She would sink 3 hours later. The fight had lasted 7 minutes. In that time, Washington had fired 75 16-inch shells. At least 9, maybe as many as 20, hit the mark. Kirishima had fired only a few poorly aimed shots. The difference was not in bravery or practice, but in basic ability. Lee had been fighting with perfect facts. Kondo had been fighting blind. Admiral Kondo's report after the fight said that American forces had shown finding and gun control skills that seemed impossible. Japanese watchers reported American shots landing with amazing accuracy, even though there were no searchlights or visible use of sight-based distance finders. Some Japanese officers guessed that American ships must have had new sight-based systems of extraordinary power. The idea that Americans were using radar for blind fire aiming seemed too far out to believe. This doubt was not dumbness, but came from their experience. Japanese rules believed that radar was not careful enough for gun control. This was true for Japanese radar. It was not true for American systems. But Japanese engineers had no way to know American technology had moved so far past their own ideas. The truth began to sink into Japanese thinking through all the proof. Lieutenant Commander Toshikazu Omi, a staff officer in the 8th Fleet, was given the job of looking at patterns in American battle winds. He gathered reports after fights from many battles. A pattern showed up. American forces regularly started shooting at distances too far away to see. American accuracy in night fights was better than what sight-based tools could explain. American ships moved as if they had perfect knowledge of Japanese spots no matter how clear the sky was. Omi figured out that Americans had finding systems far better than Japanese gear. His study guessed American radar technology was about 2 years ahead of Japanese ability. This report, given in early 1943, was met with doubt by staff officers who felt the judgment was too negative. The idea that American technology, from a nation Japanese news had called weak and poorly run, could be 2 years ahead was hard to take psychologically. But Omi was right, and the gap was getting bigger. By mid-1943, the technology difference had grown to 3 years. American destroyers built in 1943 carried radar kits better than those on Japanese battleships. American gun control systems were being built with machine-run computers that figured out firing angles automatically, getting rid of human math delays. The Mark 37 gun director showed the joining of radar with machine math. The director mixed sight-based distance finders with radar tracking, sending facts into Mark 1A computers that figured out firing angles. The system could follow targets by sight when possible, switch smoothly to radar tracking when targets were hidden, and keep finding firing answers during the changes between modes. The Mark I, a fire control computer, was a machine wonder, a room-sized collection of gears, wheels, and moving parts that kept solving math problems that showed how the shell would fly. Workers put in target facts, ship movement, wind speed, and powder heat. The computer automatically figured out gun height and direction, changing constantly as targets moved. Earlier machine computers needed human workers to put in hand-done fixes based on where the shots landed. Mark 1A took radar feedback straight into the math loops. When radar showed shots falling short, the computer automatically changed the height for the next shot. This closed-loop gun control was revolutionary. It removed the time it took for a human to react in the aiming process. The result was steady, straight shooting at distances where sight-based systems could not work. American battleships could shoot at targets 20,000 yards away in the dark or bad weather and keep hitting them at a rate that would have been thought great in daylight, fighting with sight-based tools. Japanese battleships trying to shoot back were stuck firing at the flash of the enemy's guns with no way to see where their shots landed or fix their aim. The technical quality went beyond single systems to how they all worked together on the ship. Combat information centers brought together radar facts from many places. Surface search radar gave the overall battle picture. Fire control radar followed specific targets. Air search radar found planes coming in. Workers put this information together into a full understanding that was shared with all stations through the ship's communication systems. This joining together created command advantages as great as the technical perks of single systems. American commanders fighting night battles had correct, moment-by-moment facts about friendly and enemy positions. They could move their forces based on complete knowledge of the fight. Japanese commanders, lacking this joining of systems, made choices based on small reports from lookouts who could only see nearby parts of the fight. Japanese Navy gunnery stayed dependent on human math. Distance finders helped with the figuring, but final firing angles needed practiced workers to make hand-done changes. This worked well when seeing the target allowed constant watching. It was almost useless when targets were only lines on a radar screen. The technology gap showed up in every part of Navy work. American carrier groups used air search radar that found coming plane attacks over 100 miles away. This allowed their air patrols to be directed for intercepts before Japanese planes got close enough to start their own attacks. Japanese carriers did not have this same ability. Their air patrol relied on seeing things, often learning about coming attacks only when American planes showed up overhead. The Battle of the Philippine Sea in June 1944 showed American radar strength on a fleet scale. Vice Admiral Jizaburo Ozawa led Japanese carrier forces, 9 carriers with over 400 planes. He planned to use the longer range of his planes to hit American carriers while staying out of American strike range. The plan needed Japanese scouts to find American forces first, and for Japanese attacks to avoid American air patrols during their approach. Neither happened. American radar found Japanese scouts at very long distances. When Ozawa launched his first strike wave of 69 planes on June 19th at 8:30 a.m., American radar found the group while it was still gathering over the Japanese carriers. By 9:15 a.m., American fighter directors had directed Hellcats to intercept. The Japanese attack flew into a planned defense with fighters placed by radar guidance to get the best shooting chance. The American defense was deadly in its planning. Fighter directors on the carriers watched radar screens showing friendly and enemy groups. They directed air patrols to spots calculated to get the most effective defense. Hellcat pilots got constant radio updates on enemy spot, height, and direction. They flew at Japanese groups from the best attack angles, getting surprise even in daylight. Japanese attack leaders found themselves stopped before reaching their attack spots. Groups were broken up by planned attacks from many sides. Pilots who lived through the first storm faced the heavy anti-aircraft fire from ships warned by radar with time to get ready. The proximity-fused shells filled the air with bits of metal that damaged planes, even with near misses. Of 69 planes in the first wave, only 27 lived to return to their carriers. Not one hit an American ship. Ozawa launched 3 more attacks that day. The second wave launched at 10:08 a.m. with 129 planes. American radar found the group at 10:15 a.m. Fighter directors quickly sent more air patrols and placed forces for the best intercept. 97 Japanese planes were shot down, 6 damaged American ships, none badly. The third wave launched at 11:00 a.m. with 47 planes. 27 were shot down. The fourth wave launched at 1:00 p.m. with 82 planes. 73 were shot down. By day's end, Japan had lost 346 carrier planes in the fight. American combat losses totaled 29 planes on June 19th. The numbers told a story of continuous destruction. Japanese groups were being wiped out with factory-like speed. Each wave got the same treatment. Radar found them at long range. Fighter direction guided planes to the best intercept spots. Planned attacks broke up groups. Anti-aircraft fire guided by radar tracking. The system worked no matter how many planes Japan sent or what tactics they used. From Ozawa's view on carrier Taiho, the battle was a terrible, confusing failure. Attack after attack left to hit American carriers. None got major hits. Few planes returned. Radio messages from attack leaders said they were being attacked by fighters who seemed to know exactly where Japanese groups would be. The only explanation was that American finding abilities were better than anything Japanese spies had thought possible. The mental effect on surviving Japanese pilots was deep. Lieutenant Masatake Okumiya, a carrier division leader who would later write a lot about Japanese naval flying, said in post-war writings that after the Philippine Sea fight, Japanese pilots increasingly felt they were fighting an enemy who could see them coming from impossible distances. This was not a fantasy. It was an accurate understanding of radar's power, creating battlefield omniscience, knowing everything that's happening. American technology superiority went beyond finding and gun control into the weapons themselves. The proximity fuse, developed at the Applied Physics Laboratory, began to be used in battle in January 1943. The fuse used a small radar sender to blow up shells when they passed close to planes, greatly increasing the deadliness of anti-aircraft fire. The first time it was used in battle was on January 5, 1943, when cruiser Helena fired proximity-fused 5-inch shells against Japanese planes off Guadalcanal. The results were clear right away. Hit rates against moving planes rose greatly. Shells that would have missed completely with contact fuses now blew up close enough to harm or destroy targets with metal bits. The creation of the proximity fuse showed American technical success at its best. The device had to survive the force of gunfiring, which was over 20,000 times gravity. It needed to work reliably after being put through extreme speed, shaking, and temperature changes. It needed to tell the difference between plane targets and surface noise like waves. It needed to work in rain, clouds, and different air moisture. It needed to be cheap enough for big factory making, as shells were single-use weapons. Solving these problems needed advances in many fields, making vacuum tubes tiny to create radio centers small enough to fit in shell casings, creating battery technology that could survive the shock of firing and provide power for the few seconds of shell flight, designing safe systems that stopped early explosions but turned on the fuse at a safe distance from the firing ship, engineering the factory steps that could make millions of units with steady reliability. The proximity fuse project involved over 4,000 people working across many labs and factories. Part making was spread out to lower security risks. Final putting together happened in special buildings. Quality control checked every unit before it was accepted. The system made proximity fuses at a speed of over 100,000 per month by 1944. Japanese aircrews suddenly faced defensive fire that exploded near their planes. Even when gunners aimed a little off, the mental impact was big. Pilots reported shells bursting near them with strange accuracy. The effect was made bigger because Japanese spies did not understand how the fuses worked. Pilots could not create countermoves because they did not know what was hitting them. Japanese engineers knew proximity fuses were possible in theory. Many research groups looked into the idea, but building them needed factory ability, careful making, and systematic quality checks at large scales. Japanese industry could not match this while also making ships, planes, and regular weapons. The proximity fuse was not just one invention, but the product of a whole factory system made for high-tech mass production. By late 1944, the technology difference had become so serious that American and Japanese Navy forces were basically fighting different wars. American planning was based on full radar sight, automatic gun control, and connected command through combat information centers. Operations were designed around these abilities. American rules said night fights against surface ships were routine because radar made the dark tactically useless. Japanese planning assumed that most fights would be decided by seeing things and hand-aimed guns. Night operations were considered very risky, needing specially trained forces because Japanese abilities stayed mostly sight-based. This meant Japanese commanders planning actions had limits American commanders had removed through technology. The Battle of Surigao Strait on October 25, 1944, showed the huge difference. Vice Admiral Shoji Nishimura led a force of 2 battleships, 1 cruiser, and 4 destroyers through Surigao Strait in darkness, trying to attack American landing forces at Leyte Gulf. His force was found by American patrol boats at 2:36 a.m. Radar followed Nishimura's progress as he moved up the strait into a trap. Rear Admiral Jesse Barrett Oldendorf led American blocking forces, 6 battleships, 8 cruisers, and many destroyer groups placed across Nishimura's T. This was the classic Navy move of bringing maximum gun power against a moving line of ships. But this was crossing the T with radar guidance. American destroyers launched torpedo attacks guided by radar tracking. American battleships began shooting at about 20,000 yards with main guns aimed by radar fire control. Nishimura's force was destroyed completely. Both battleships sunk, the cruisers sunk, 3 destroyers sunk, the 1 remaining destroyer ran away, damaged. American losses were very small. The battle had been less a fight than an execution, with Japanese forces moving without knowing into set spots where American radar-guided weapons got almost perfect surprise and terrible accuracy. Nishimura had been sailing blind into an enemy who watched his every move. Japanese lookouts never saw American battleships until the shots began landing. The first sign Japanese forces had of American presence was shells exploding among their ships. They tried to shoot back, but had no clear targets. American battleships stayed at distances where seeing them was impossible in the dark. The fight lasted less than 30 minutes. It showed that against radar-equipped enemies moving through tight waters at night was suicide. Lieutenant Commander Omi, studying the battle later, said that Japanese forces had tried tactics that would have been smart against an enemy with the same technology limits. Against radar-equipped forces with automatic gun control, those same tactics were deadly. The lesson was clear, but it came too late to change Japanese battle plans. The full numbers story of American factory output in shipbuilding became clear only after the war ended. Between December 1941 and September 1945, American shipyards made 28 fleet carriers. Japan built 17 carriers of all types during the same time, and most of these were changed from other ship types rather than built for one purpose. American production included 71 escort carriers, small carriers built on trading ship bodies, made for submarine fighting and landing support. These ships, less powerful alone than the big carriers, gave air power spread across the Pacific. Japanese production included no similar ships, as Japanese rules focused on big carriers for one decisive fight, rather than air power spread out for constant operations. American shipyards made 8 new battleships during the war, all of the Iowa or North Carolina class. These ships had radar and fire control technology from their first build, with plans made for joining electronic systems. The North Carolina class, approved before war started, were updated with better radar while being built. The Iowa class included lessons learned from early war fighting, with electrical systems and inside layouts made around radar joining from the very start. Japanese battleships Yamato and her sister Musashi showed the peak of old battleship design 64,000 tons big. 18-inch main guns shooting shells weighing over 1 ton each. Armor made to stop any shell fired by any existing battleship. These ships were amazing works of engineering, the biggest battleships ever made, but they were built based on ideas that turned out to be old-fashioned. Their design focused on sight-based distance finding with light-based equipment of amazing quality. Their fire control systems depended on trained workers doing hand-done math for the answers. They carried radar as an add-on, equipment put into spots not made for it. The joining was weak. The ability was limited. Against radar-equipped enemies, Yamato and Musashi's advantages in armor and weapons were canceled out by their inability to aim guns well. The difference showed 2 ways of thinking. Japanese design put first the perfect use of old Navy fighting. American design put first the joining of new technologies that changed what sea war was. Japanese battleships were built to win classic gunfights. American battleships were built to fight connected battles where radar-guided guns hit targets at distances sight-based systems could not reach. The difference spread through every class of ship. 377 American destroyers compared to roughly 63 Japanese destroyers. American destroyers late in the war carried radar kits that gave finding, tracking, and gun control abilities close to those of pre-war cruisers. Japanese destroyers stayed mostly gun and torpedo ships with limited electronic ability. 232 American submarines compared to 126 Japanese submarines. American submarines had radar that allowed surface attacks at night with very little risk of being found. Japanese submarines relied mainly on the periscope, limiting their effectiveness against ready enemies. American escort carriers, 71 ships built on trading ship bodies, gave air power spread across the Pacific. These ships worked to support beach landings, did anti-submarine searches, and gave air cover for supply groups. Japanese production included no similar ships. Japanese rules stayed focused on big carriers for one decisive fight, rather than spread out air power for long-term operations. The numbers difference was bad, but numbers alone didn't tell the whole story. An Essex-class carrier built in 1944 had more fighting power than 2 or 3 Japanese carriers from earlier in the war. An American destroyer from 1944 could do jobs that would have needed a cruiser in 1941. The combined effect of numbers and technology strength meant American forces were beating Japanese forces by bigger gaps as the war went on. An Essex-class carrier, the main ship of American carrier forces late in the war, showed the joining of factory power and new technology. Standard weight 27 out 100 tons, full load weight 3,900 tons, length 872 feet, space for 83 to 108 planes depending on the types. But the numbers didn't show what made Essex-class carriers so powerful. Each carried many radar systems giving full awareness. Air search radar found planes over 100 miles away. Surface search radar followed ships to the horizon. Height-finding radar figured out how high detected planes were. Fire control radar guided anti-aircraft guns. This electronic sensor set, connected through combat information centers run by experts trained in radar reading, gave Essex-class carriers battlefield knowledge impossible for earlier carriers. 24 Essex-class carriers were built. 32 had been ordered, but 8 were canceled after Japan gave up. Of the 24 finished, 17 saw fighting in World War II. These ships provided the hitting power that destroyed Japanese naval flying, supported beach landings across the Pacific, and finally hit Japan itself. The carriers fought with a boldness that would have been careless without the technology edge. American carrier groups often operated within reach of Japanese land-based planes because radar gave enough warning to plan a defense. Air patrol could be kept over the ship groups and guided to intercepts by fighter directors watching radar screens. This allowed American carriers to work in waters Japanese carriers avoided as too risky. Japanese carriers, late in the war, were forced to stay in spots where land-based air cover could protect them since their own radar couldn't. The roles had flipped. Japanese forces looked for cover. American forces moved freely. Sure, their technology gave them a clear advantage, no matter how many enemy ships were in any one area. The technology change was so complete that by war's end, American Navy forces fought with assumptions Japanese forces could not match. Night operations were normal for American ships with radar. Japanese forces still treated night operations as needing special conditions and specially trained crews. American carriers operated aggressively close to enemy bases. Japanese carriers operated defensively under land-based air cover. American battleships hunted enemy warships. Japanese battleships were moved to less important jobs, their main guns mostly useless against enemies who could strike from distances too far to see. The lessons Japanese officers took from the war would shape their understanding of modern fighting. Lieutenant Masatake Okumiya, who lived through the war and became a lieutenant general in the Japan Air Self-Defense Force, wrote a lot about Japanese experiences. His post-war writings, including co-authoring Midway, The Battle That Doomed Japan, looked at how being behind in technology had constantly weakened Japanese battle advantages. Okumiya had finished the Imperial Japanese Navy Academy in 1930. He served as a carrier division leader during the war, flying missions and planning actions. His view mixed battle experience with big-picture understanding. After the war, he became one of the most important people explaining Japanese Navy history to American audiences. His main point was that Japanese forces had started the war with tactics and training that were great for the technology level of 1941. American forces had consistently raised that level through constant technology use. By 1943, Japanese battle advantages in seeing things and hand-aimed guns were useless because fights were being decided by radar and automatic gun control. Japanese forces were fighting with old ways against enemies who had changed the fundamental rules of combat. Okumiya stressed that this was not a failure of Japanese bravery or battle skill. Japanese pilots and sailors fought with courage throughout the war. Unit strength and fighting spirit stayed high, even as equipment broke down. But spirit could not beat a systematic technology disadvantage. The bravest pilot could not beat radar-guided fighters that stopped his group before it reached attack range. Lieutenant Commander Omi, whose wartime spy work had correctly seen American technology strength early in the war, was questioned a lot by the United States Strategic Bombing Survey after Japan gave up. Survey questioners described him as the most reliable and correct source of facts found in Japan. He gave detailed studies of Japanese operations, big decisions, and guesses about American abilities. Omi finished the Imperial Japanese Navy Academy in 1922. He served as a staff officer in various fleet commands, jobs that gave him access to battle facts and planning. His skill in looking at facts made him priceless to American questioners trying to understand Japanese decision-making. His post-war writings for the United States Naval Institute provided a detailed Japanese view on the technology gap. His article, Japanese Commentary on Guadalcanal, published in 1951, gave insights that corrected American understanding of several fights. He later worked as a consultant to Admiral Samuel Eliot Morrison for his multi-volume history of United States Navy actions in World War II. Omi's view was that Japanese Navy forces had been beaten not by lack of courage or bad tactics, but by a systematic technology weakness that made individual battles increasingly impossible to win as the war went on. He guessed that American radar and fire control technology had been about 2 years ahead of Japanese similar items in late 1941. By mid-1943, this had grown to 3 years. By war's end, it had grown to at least 5 years. The gap got wider because American factory and research ability allowed fast updates and fixes, while Japanese ability was overwhelmed just trying to use earlier systems. American radar progress went through many new versions during the war. Japanese radar progress struggled to get the first version systems into widespread use. The compound effect of technology progress meant initial advantages grew very quickly. Omi noted that Japan's basic mistake was not failing to invent modern technology, but failing to understand that modern factory-based war needed the technology level to be constantly moved forward across the entire military structure. Single brilliant systems were pointless if they could not be made in huge numbers, widely used, and constantly upgraded. American victory came from planned technology use on a large scale, not from single technical breakthroughs. This understanding came too late to change the war's end. For American Navy forces, the war proved a way of fighting that would shape American military rules for decades. Technology could create advantages so strong that old factors like individual bravery, unit training, and battle skill became secondary concerns. Investing in technology superiority brought benefits that were bigger than any other military investment. The officers who fought the Pacific War returned home certain that America must never allow technology gaps to appear against America. The radar and fire control systems that beat Japan led straight to guided missiles, computer battle management, and network-centered warfare. The main idea stayed the same across generations: remove humans from decision-making where machines can do better. Make everything automatic that can be made automatic. Join systems for combined effects that are greater than the sum of the single parts. The Japanese Navy of 1941 had been a powerful force built on many years of experience and training. Officers were experts who had spent careers mastering their jobs. Sailors were trained to levels that were better than those of most Navy forces. Equipment was new and well kept. Tactics were complex and well practiced. By traditional standards, the Imperial Japanese Navy was one of the best naval forces in history. But traditional standards proved not enough when the nature of combat changed. Experience and training built for one technology age proved too little when the technology age shifted. The Americans had not simply beaten the Japanese Navy. They had made the kind of navy Japan had built obsolete. The fast battleship, the massive torpedo attack, the night fight with better sighting gear, all the parts Japanese rules valued became secondary to the overwhelming advantage of seeing the enemy when the enemy could not see you. The battleship Kirishima had been modern and strong by 1941 standards. Her sight-based distance finders showed the best technology money could buy. Her crew had trained for years in sight-based gunnery and night fight methods. None of this mattered when she faced an enemy who followed her through electronics she could not find, figured out firing answers through machines she could not match, and hit with accuracy her sight-based systems could not achieve. In 7 minutes of radar-aimed gunfire, USS Washington showed the clear power of technology superiority. The fight was not close. It was not a battle between equals where bravery or skill tipped the balance. It was the systematic destruction of an enemy who lacked the technology to fight back well. Kirishima's crew fought bravely. Her officers made battle-smart choices based on the facts they had, but they were fighting blind against an enemy who could see perfectly. This was the main lesson of American technology strength in the Pacific War. Victory belonged not to the Navy with the most courage or best training, but to the Navy that successfully used advanced technology across the whole force. Individual heroism, battle brilliance, and professional excellence stayed important, but they could not overcome systematic technology weakness. The Americans had jumped ahead, and the gap grew wider throughout the war. Japanese forces fought with growing despair as it became clear they were outmatched not just in numbers, but in a basic way. By 1945, Japanese Navy forces were forced to kamikaze attacks because normal tactics had proved useless against enemies whose technology made them almost safe from old sea combat methods. The Japanese Navy fought until the last day of the war. Officers and men showed courage that earned respect even from enemies, but courage could not cross the technology divide. The future arrived November 15, 1942, in the darkness off Savo Island, when Washington's radar locked onto Kirishima and showed that sea warfare had started a new era. That future belonged to the nation that had built it, used it, and constantly improved it through planned factory work that turned lab successes into fleet-wide abilities. The Americans had not just won the sea war, they had changed what sea warfare meant.